Today we have with us Steve Kilston, and starting with discovering a comet at age 21, for over half a century, Steve Kilston has applied astronomy in academic research and teaching, planetarium and public lectures, radio programs, and national and international aerospace projects. At Hugh, Lockheed, and Ball Aerospace, he designed and promoted space-based telescopes, including IKONOS, I-K-O-N-O-S, probably said that wrong, the satellite called in the New York Times one of the most significant developments in the history of the space age. Its high-resolution commercial Earth imaging camera made possible many new technologies, including Google Maps and GPS automobile navigation systems. Now he was retired in Cottage Grove, where he hosts the Wisdom Seekers Club. Steve earned a BA from Harvard. His thesis under Carl Sagan was A Search for Intelligent Life on Earth, and a PhD from UCLA. His dissertation on the nature of the carbon stars proved stars manufacture life's main chemical elements. Please welcome Steve Kilston.
Thank you all. I hope you can hear me now. I have a picture here for you showing the sky from Australia. Since it's the southern skies, you may notice if you look on the left that there's a constellation of Orion, but it looks upside down. And to the right of that is the big bright star Sirius and Canopus and the large Magellanic Cloud and the small Magellanic Cloud. You're seeing the universe, but of course, you're also seeing the Earth in Australia there. And it's very clear from this picture how much the Earth is part of the universe. Slide. So I want to remind you all that historically, humans believed that our world was the center of the universe, and that sort of gave us our own central place. That was a comforting idea. But astronomy found over millennia that the Earth is just one of the sun's several planets, and there are other stars and galaxies that are very, very distant, so that we're not that special in a way. And when you see the size of the universe, a lot of people say things like Pascal said hundreds of years ago, the eternal silence of these infinite spaces frightens me. But is our cosmos really cold and hostile? Are we really having the tiny little existence here on Earth in this gigantic universe? Next slide, please. This is just a funny cartoon. As an astrophysicist, if my work helps just one person feel like a tiny, insignificant speck lost in a cold, uncaring universe, then I'm doing my job. Okay, and that's what some people might think of astronomy or astrophysics as. But go ahead, next slide, please. Just to give a little personal history, my father took me to the public library almost every 2 weeks of my youth, and right near the beginning, he found me a book on supergiant stars like Betelgeuse. Of course, like all kids, I was fascinated by big things like dinosaurs, but also by giant stars, that could have 1 million suns fit inside them. So by the time I was 11, a friend let me use his telescope to see spots on the sun and double stars and things. And then when I graduated high school, I studied astronomy for 12 straight years in college and graduate school. That's more than most people do. I learned how to program computers and how stars are put together, basically. And I figured out some stuff myself that added to this knowledge about how stars burn their nuclear fuel to create heavier chemical elements. My work with Carl Sagan was looking at pictures of the Earth taken with the first weather satellites. And those pictures were designed, of course, to look for clouds and weather, but we also were able to look for things like the Great Wall of China and the pyramids and other things. We could not see those. We could not see those with the resolution of those satellites. That was about 1 kilometer. And that was to compare with the first mission to Mars called Mariner 4, which took similarly detailed pictures, in other words, not very detailed. So the answer from the work I did with Carl Sagan was that not seeing existence of life or intelligent life on Mars with those pictures the Mariner 4 took didn't really prove anything, because we couldn't see life on Earth with the same kind of pictures. I heard a very interesting lecture when I was in graduate school by a man named Benjamin Peary about how some of the stars showed the presence of an element called technetium, which has radioactivity that makes it live only about a few 100,000 years. The stars live a lot longer than that, so that therefore this particular chemical element must have been made in the stars. It couldn't have been born with, the stars couldn't have been born with that element because it would have disappeared already. Next, please. So this was from my doctoral work. This is a picture of one small part of the red spectrum, the red colors of a star. And you can see here a line which indicates the light from the star, the light going up and down as you change the color slightly. And then the dots on there, if you can see those, are my attempt to match those colors by figuring out how many chemical elements were in the atmosphere of that star, how many different atoms of various elements like iron and yttrium, and in this case, the molecule called cyanogen. And that tells me how much carbon was in the star. And I showed that they had to have so much carbon in them to give this kind of spectrum that they must have made that carbon themselves. So this was proving that stars actually make the chemical elements that are in life and in our own bodies. Next, please. This is the way that stars make carbon. Our own sun at the moment is turning hydrogen into helium. And that's what gives us the light from the sun and the warmth and keeps us here from freezing to death. But in the later stages of the sun's life and in some of these other stars, the helium is turned into beryllium and then into carbon. So this is the process by which the sun and other stars will make carbon. Go ahead. Now, here is an example of a dying star, a carbon star that is sending its material out into space. After it's already made the carbon, we know it has carbon from looking at its spectrum, and now that material is leaving the star, and our own solar system was formed from material that was enriched by stars that existed previously to our solar system, similar to this one, that then put that energy and that material out into the universe. This is the process that enables life to get started in our universe, because first the stars have to make the right chemical elements. Next, please. These are the chemical elements in the periodic table that you've all probably studied in high school. But the different colors show where the chemical elements are made in the universe. And the ones that are shown in green there are made in the kind of stars I studied, the carbon stars. They're made in the later stages of stars' life, and they evaporate off into space, off of that star. And some of them, you'll notice they're like carbon and nitrogen, are essential to life. So some of the others are made in exploding stars or in neutron stars, which are at the end stages of supernova. And some, like hydrogen and helium, were formed at the beginning of the universe. But the green ones are the ones I was interested in, that are made primarily in these kind of stars. The ones at the very bottom right are only artificial, and we have to make them here on Earth in some of our accelerators and other kinds of nuclear machines that we have. Okay, now here are some nebulae where the stars that made the chemical elements have sent their material off into space, and gravity has pulled a lot of it back together. And it's pulled this enriched material, sort of fertilized material, with new chemical elements into it to start forming new stars. The stars in the middle of this are just being born, and they are lighting up the rest of the nebula around them. These are stars much younger than our sun and solar system, and we can watch this process going on as new stars are formed throughout our galaxy. Okay, and of course, our whole solar system, not just the sun, but all the planets and comets and asteroids and everything else in our solar system, were made of this enriched material. They have, with the sun being formed, blown most of the gases and dust away so that only the planets are left primarily. And we're that little blue one right at near the top of the screen there. You can see we're not that big compared to the other planets or the sun. And then the human body as you know, is mostly water, and it has protein and fat and other stuff like that. But the chemical elements in our body are shown on the left and right sides here, and we're made mostly of oxygen by weight, because water is mostly oxygen by weight. And the second most mass that we have in our body is carbon. So you see how carbon made in stars is very important to us. And the other elements are shown there. So this is an illustration of the fact that all the elements that make up our bodies, and myself who is talking to you right now, are these things, part of which had to be made in stars, most of which had to be made in stars. So just to review, in the galaxy, gravity and shock waves from other stars push massive amounts of gas and dust together to form new stars. You saw some of those already. Nuclear reactions in the stars provide new elements, and they also provide energy. The energy helps resist the crush of gravity, so the star doesn't shrink for a long time. And our sun will be going on for at least a few more billion years with this balance between its nuclear reactions in the center and the gravity that pulls it close together and keeps it hot in the center. All right, and also this material comes to the surface of the star, where I was able to observe it and prove how much carbon the stars have made. The old stars, therefore, are enriched with these new elements. When they die, they let that element go off into space, either sort of evaporating off or exploding off. And that material can form new solar systems like our own, showing that the atoms inside us came from earlier stars, and we are all made of stardust, as even Joni Mitchell said in one of her songs there. And the Stardust Hotel, which was named long before people knew this, and of course the song Stardust by Hoagy Carmichael, all were made before people realized that we are made of that stardust. So some people wonder, well, that's all right, what other solar systems might look like. People have made drawings of that, but we don't know exactly what they look like yet, although we have found them. And that's the big change since I was in school. When I was in school, nobody knew of any planets outside our solar system. Now we know about almost 6,000 of them. One of the things I worked on when I was working in aerospace was called Terrestrial Planet Finder, and we spent a lot of time thinking about what planets and other solar systems might look like and where they would be able to support life. And it turns out that every star has around it a habitable zone. If you're too close to the star, you can't have life, it's too hot. If you're too far, it's too cold. And if you're just right, like Goldilocks, in the right place, you will be able to have the temperatures that allow water and life to exist. So the habitable planets we were looking for, most of them we know now have been found by this spacecraft that the company I worked for in Colorado built. It's called Kepler. And it has discovered over 2,600 planets in other solar systems, including the first ones that are like the Earth. And it showed that there are more planets in our galaxy than there are stars. Kepler found that about 1 in 5 stars like the sun seem perhaps to have an Earth-sized planet in the habitable zone that might be capable of hosting life. And if you consider how many stars are in our galaxy, the Milky Way, there may be perhaps 10 or 11 billion potentially habitable Earth-sized planets. And even more if we include planets that go around other kinds of stars, like the many red dwarfs that are out there. But we have to know much more about a planet than just its size and its orbit to be sure that it really is habitable. There are lots of other things. There's a book I recommend to all of you called Rare Earth that tells about how hard it is to have a planet that has life. I'm sure you all heard recently about the James Webb Space Telescope that was launched on Christmas morning. That is a fantastic new telescope that is made up of segments of mirror, 18 different segments to make one huge telescope that's going to have a mirror effectively over 20 feet across and is going to be able to see many other planets, we hope, and measure the chemicals that are in them. Also seeing many things about the beginning of our universe. it was launched successfully. Now we're planning other telescopes. Almost all the big ones will have these same kind of segmented mirrors, and maybe we'll have one as big as a football field by the year 2050 or so. That's planned, a possibility here on the ground. Then there's a plan for other telescopes in space that might have multiple spacecraft all working together, again with these segments in them, joining them into one gigantic telescope that is spread over 1,000 kilometers in diameter, an area bigger than the state of Oregon. And that might have the resolution able to show another planet in another solar system with a picture such as the one shown here, a picture that might show us if it has continents and oceans like our Earth does. When I studied this kind of stuff and was planning these kinds of space missions, I began to think, if we find a habitable planet, what are we going to do about it? And so I came up with my idea for the ultimate project, something that's going to take us at least 500 years, probably a lot more to do. Next slide, please. This is my idea for a spaceship to go to other stars and maybe to a good planet around those stars. It's a big spaceship. It's 2 kilometers long, 2 kilometers in diameter. It has about 10 decks of living space and working space. It will have parks on it. It will have all kinds of things. It will basically be a civilization on board a spaceship. It will have 1 million people on it, and it will weigh 100 million tons and cost probably at least $50 trillion. That might seem like a lot of money, but remember that building it over a period of 100 years or so, that's less than our US defense budget that we spend over that time. I propose that it might be launched as early as 2500 AD, and that it would spin around about once per minute. When it spins around that fast, everybody in the living spaces there would have centrifugal force that's equivalent to gravity, the same kind of gravity we have on Earth, so they wouldn't have to worry about their bones losing calcium or other stuff like that. And I think that this could be built. Obviously, we have to develop lots and lots of technologies. Next picture, please. This shows the size of the spacecraft relative to the Great Pyramid of Cheops in Egypt. Okay, it's a very, very large spacecraft. But that's what you'd want to do, because you don't want to have too few people where everybody gets bored with each other after a while. You could constantly be meeting new people on this spacecraft every day of your life. I went through and calculated all the things necessary for this to really be something that could work, and how much fuel it had to have, and how much propellant, something like 12 million tons of fuel and propellant, how much energy would be available for supporting the ship, you know, how it would keep people alive with electricity kind of stuff. And all that is calculated here. By the way, this would take about 10,000 years to get to a fairly nearby star. 10,000-year voyage is one good reason to have such a big ship, so that people would be able to have many generations. It would be enough people so there wouldn't be a big problem with interbreeding. And on such a ship, it's called a generations ship, you'd have to maintain it for a very long time. But of course, you wouldn't want to lose anything, like lose the air and lose the water. You'd have to recycle everything. And that a lot of problems have to be solved, as I said, to make this work. I'm not saying it's easy. Next, please. But I decided it would take quite a long time. You know, computers have changed. Can you all remember the computers that you had, let's say 30 or 40 years ago? And what you have now in your pocket with a smartphone? Things have changed a great deal. And I hope that technology will keep changing over the next 500 years. So the very first thing we need is to have an engine that is maybe a fusion powered engine. That's what I've assumed. And just this last month, the first human fusion machine here on Earth was made that produced more energy from fusion than it took to make it work. That's called break even was reached, break even energy, and that was achieved just this last month. So a lot of other things have to be designed and built and figured out. But I figured that the design of such a spaceship in detail would probably have to take another couple hundred years from now, and we demonstrate all the technologies and build colonies in our solar system, space colonies, before we ever built this ship to show that it would work here. And we'd assemble the materials and launch a 100-year test, a shakedown cruise, they usually call it, for about 100 years, starting the year 2400, so that by the year 2500, we'd be able to launch to another star. That's a long schedule. Astronomers tend to think in terms of long periods of time. Go ahead. Next slide. The biggest challenges are psychological and social and environmental. We have to figure out how people can live together in harmony. You all see that that's not happening right now on Earth, whether it's in Ukraine or whether it's in our own government or on the bridges from Canada to the United States. People have to learn how to get along better and to work together better to make such a project work. And if it does work, we can go not only to another star, but we could build other spaceships when we get to those stars and continue populating other planets in the galaxy, so that in about 40 million years, that sounds like a long time, but it's only 1% of the age of our galaxy, actually much less than 1% of that. So we're proposing to build into our galaxy life in the whole galaxy that would carry forward the things that life can do, such as making a culture, making beauty, making intelligence, making knowledge. All those things would develop across our whole galaxy if we're able to get to another star. Now, the last part of this talk is going to be much less scientific, but it's going to build on the fact that not only do we have stars inside us right now, you are listening to me because of stars inside you and me talking, but our universe basically is learning to experience and feel and learn and act because we have the ability to have intelligence in us and to have life that stars have had, and we are able to feel our universe. I don't know if you understand or think that you are feeling our universe, but at every moment of your life, you are feeling our universe. And this will be part of what makes it possible for us to go to other stars if we understand how we feel our universe. So I want to talk about touch a little bit here. When you touch something, that's probably the earliest feeling you ever had was touch. You probably were feeling the sense of touch inside the womb. We also feel the universe every time we go outside and feel the warmth of the sun, right? That's obvious. You're feeling the universe then. That sun is powering almost everything on the Earth, and we're in contact with it. We're in contact with our star and all others that have produced the stuff inside us. And astronomy's maybe biggest lesson that is taught over the last 100 years is not the Big Bang or the black holes or anything else like that. Astronomy has taught us that our universe is thoroughly interconnected and interacting. You probably all learned about Newton's third law, that every action has an equal and opposite reaction. So out of that law, I wanted to propose two other rules. The super golden rule, do unto our universe as you would have our universe do unto you. And the super Kennedy rule, after John F. Kennedy's inaugural speech, ask not what our universe can do for you, ask what you can do for our universe. I think we have to understand those two rules and learn to maybe behave that way. And that includes thinking that our own selves, our own ego, and our own independence are in many ways illusions. We are a two-way connected universe, and feeling that universe is feeling reality. This is a little bit hard to understand, but I think that feeling our universe demands that we feel our universe feeling us and feeling everything else. Try to think about that for a minute. You are feeling our universe, feeling things. If you think of yourself, that creates division, isolation, and often frustration. If you think of yourself as separate from things. But if you think of and you feel touching makes things flow, it adds to circulation, health, and the pleasure of belonging, if you feel in contact with things. So I am asking you to be our universe and to feel our universe, to touch it and to let it touch us. And I don't think you can ever be lonely if you feel yourself really a part of the universe. When you throw or catch a ball, you are our universe playing with the ball. The ball, of course, is part of the universe too. And you have the universe's power and confidence. You don't have to do things all by yourself. When you think it's a real tough job, just remember the universe is doing that job. Can you feel being our universe? Can you view yourself as the universe? Now, you may wonder, how can I be the whole universe? Well, it's a little part of your brain that thinks of you, and yet you have the whole body around it, that the body that the brain thinks is it. So that's another way of thinking about yourself being the universe. Okay, and through you and through me, our universe has become conscious of itself. Through life, the universe is feeling, choosing, dancing, caring, loving, adventuring into the unknown, delighting in things, building things, making mistakes, crying and laughing. Our universe is doing all those things because it has made the chemical elements that make life, and in our case here on Earth, people. Here's a picture which sort of shows that you have the universe inside you and you're carrying with you all the parts of the universe that are making new stars and made stars in the past. These are some of my favorite pretty pictures of the universe that the Hubble Space Telescope took. Here's a few other thoughts. You can't fool our universe. You cannot fool it. Everything is all connected. So just allow yourself to be the universe. The universe doesn't judge itself. The universe is not about winning or losing, and nobody's keeping score. And if you can see yourself as the universe, you can see the universe as being on your side, because you are the universe. The famous Buddhist philosopher who died recently, Thich Nhat Hanh, said, enlightenment is when a wave realizes it is the ocean. That's how I'd like you to think of yourself too. Finally, in summary, this is my wife and me on an island of Tahiti. All objects and ideas are totally interconnected and interdependent. That's something the Rotary Club should really like, I hope. We help our universe feel, think, increase beauty, and have purpose. And feeling our full connection with our universe strengthens us. Next, please. So I thank you all very much for listening. And if you have any questions, I'll be happy to respond to them.